right. I'm going to go back just a couple of slides to make sure that we're sort of picking up when I'll kind of pick up where we start to talk about nonlinear relationships. So last time we talked about, in general, multiple linear regression, and then we talked about when you have interaction terms. So if you basically have different slopes dependent on some variable. And now we're going to talk about another case where you might have nonlinear relationships between your x and y and how you could account for that in your linear model. There's several ways to do this, but for this class we're going to focus on polynomials as a way to address this. So basically we're just going to add higher order terms to our model in order to account for the potential nonlinear relationship. And so the reason why this is going to be important, which we sort of started to get into at the end of class last time, was that when we're adding these polynomials, we're basically adding functions of our x variables to our linear model, such that we no longer can use our traditional framing for how to interpret a beta coefficient. So traditionally, we interpret these beta coefficients in multiple linear regression as a 1 unit change in x yields a beta hat change in y, holding all other variables constant. But if the other variables in the model are actually functions of the variable that you're interested in, you no longer can hold the one you're interested in. You can't vary that while holding a function of it constant. That's not possible. So we're going to have to think of a different way to sort of interpret those beta coefficients. And so that's what we're going to get into for this section. So going back to that diamonds data, if we're interested in predicting total price from carrots, is this an example of inference or prediction? Prediction, yes. And if we were instead interested in understanding the relationship between carrots and total price, what would we be doing? Inference, yeah. So ultimately, the model that you're fitting, the way you fit the model, the linear model, can be the same in either case, but kind of what you get out of it will be different depending on your goal. And so with inference, we tend to care about those beta coefficients, and that's what we're going to be in this case, we will focus on those. So when I plot here on the x-axis carrot and total price on the y-axis, does this look like the linear? If I just were to do a simple linear regression model, do you think the linearity assumption would be met? No, because it doesn't look like there's a linear relationship between x and y. So this is where I fit my simple linear regression model. Here I drew the line for this model. And I end up, the problem here is that basically we're systematically over-predicting, or under-predicting rather, for diamonds in this range. So all of these have values, all these data points, the values are actually greater than what we're predicting. We're predicting along this blue line. And similarly, for these mid-range diamonds, we're basically systematically over-predicting their price, and so the blue line falls above most of the actual dots. And then for these these diamonds with a really large number of carrots, we're systematically under-predicting again. And so because it's not a linear relationship, the line is not a very good estimate for the relationship between these two variables. So instead, we could add a polynomial term. So in this case, we're adding a quadratic term, which just means we're squaring that x variable. The way we do this in R is by so this is our x variable of interest is carrot. So we've got carrot plus carrot squared, where I've wrapped the carrot squared equation in this capital I function. And that's just to let R know that when I'm saying carrot squared here, what I want it to do is apply this actual function to this variable within this data set. So this is sort of a shorthand way of doing it. A longer way to do this would be to add a new column to my data frame called carrot squared that consisted of the carrot column squared, and then I could use that column here as well. That would also get me the exact same answer. So when I do that, I get this new blue line here, and this looks like it nicely fits the data. And so we no longer have this problem of kind of systematically over or under predicting. We're doing a pretty good job of predicting kind of right on target. So what this sort of gets at as well is one of the questions on your homework, or what are the assumptions of multiple linear regression? The assumptions for multiple linear regression are the same as that for simple linear regression, except now we have basically, for simple linear regression, we said that x and y have to have a linear relationship. But once we are kind of moving into the multiple linear regression space, it's not that x and y have to be linear, it's that the function of x that we're modeling, along with the other kind of covariates that we've included in our model, that needs to be linear. So basically, the line that we end up fitting needs to match the shape of the data. So we no longer need x and y necessarily to be linear if we account for the nonlinearity in the model itself. So this is still a linear regression model because the format of it is still a linear combination of these variables, but the variables that we are using, some of them are functions of other variables that kind of allow for these nonlinear type shapes when we actually predict values. All right, so what is the equation of this relationship as I've modeled it here? So if I have total price as my outcome, what am I modeling here as where in this with this LM function? If we put hats on it, then we're gonna put a little hat there, which is fine. We do that. Beta hat 0 plus beta hat 1 times caret plus beta hat 2 times caret squared, exactly. Very good. So we can write this with beta hats, or we could write it like I have here without the hats, and then we would need an epsilon or an error term. So what would be the interpretation of this beta hat 1 in the context of this model? This is kind of a trick question based on what I said before. So if we didn't have this squared term, how would you interpret beta hat 1? So if this was just a simple linear regression model with just caret, how would you interpret that beta hat 1 value? Yeah, exactly. So for every 1 unit change in caret, the expected total price is expected to change by beta hat 1. If we had, instead of this beta 2 caret, if we had beta 2 times something like depth, so just another variable independent of caret, how would you interpret that beta 1 now? So like if this was the model, total price equals beta hat 0 plus beta hat 1 caret plus beta hat 2 depth. How would you interpret the beta hat 1? Yeah, it would be the same except you'd say holding depth constant. So you'd say a 1 unit increase in caret yields an expected change in total price of beta hat 1 holding depth constant. But the problem with this first equation is that we can't vary caret and hold caret squared constant, so we can't use that same interpretation. And maybe a visual of why this won't work is if this is my model, so if I include a squared term, then my line that I'm drawing is going to end up looking like this quadratic line here. And so if we're talking about 1 unit changes, so here I've got a little picture where I have from 1, 2, 3, and 4. The change that we're referring to is basically if we go from 1 to 2, what is this difference in y? If we go from 1 to 2 in this picture, we've got a difference of whatever this is in y. If we go from 2 to 3, which is also a 1 unit change, we have this difference in y. If we go from 3 to 4, we have this difference in y. So you'll see that the difference in y changes dependent on where you started in your x. And so this is going to be true if you have any kind of other function of your x. So it won't be this same relationship if you had a different function of x here. But you'll always have, if you include x in some function of x, your 1 unit is going to be dependent on where you started. And so we can no longer, when we're dealing with like polynomial terms, we can no longer interpret these betas in the broad sense in terms of 1 unit changes. We have to specify where we're starting and where we're going. So just to sort of restate what I said here, typically in multiple linear regression, the interpretation of a beta hat is a 1 unit change in x yields an expected change in y of beta hat holding all of the variables constant. But it's not possible to change caret and hold caret squared constant. And so when you have a polynomial term like this, or a function of one of your x variables, and you're interested in the interpretation of the coefficient of one of those variables, you need to specify the specific values that you're changing between, as opposed to be able to make this general statement of what would happen if you change 1 unit. So let's do this as an example together, and I think this is where we left off in class last time. So if I were writing out the equation here, if I were to fill in my betas, I could say beta hat 0 is negative 522.7, beta hat 1 is 2386, and beta hat 2 is 4,498.2. So if we're interested in the expected change in total price for a 1 unit change in caret changing from 0.8 to 1.8, how could I get that using these values? Yeah, I could plug in exactly 0.8 and 1.8. So here I could plug in 1.8 and 1.8 squared for caret and caret squared. And then I could subtract that from when I plug in 2386 times 0.8 plus 4498.2 times 0.8 squared. And so you'll notice first that like these are going to cross out because these are the same in both cases. So all we're worried about are these pieces. And it turns out we could actually like simplify this a little bit. We could recombine these terms. So it's going to be 2386 times 1.8 minus 0.8 plus 4498.2 times 1.8 squared minus 0.8 squared. So just to sort of show you that these are the same here, I've done it the first way as kind of with this full equation where we subtract the 2, and I get 14,081.32. And then the second is when I've sort of recombined the terms, should be written like this, and we get the same answer, that $14,081.32. And so the general form of this is that we can change this to basically beta hat 1 times b minus a plus beta hat 2 times b squared minus a squared, where we're interested in a change from a to b between these two. So what does this mean? How do you interpret this $14,081.32? What does that mean in the context of this model? Exactly, yes. So a 1 unit change from 0.8 to 1.8 in caret yields an expected change in total price of $14,081.32. Okay, now let's do it for 1.8 to 2.8. So what would I change if I were trying to get that? Yeah, so I would change this to be 2.8 minus 1.8 and this to be 2.8 squared minus 1.8 squared. So we know that this one is equal to 1481.32. And if I change it to 2.8 and 1.8, I would do 2,386 times 2.8 minus 1.8 plus 4,498.2 times 2.8 squared minus 1.8 squared. So I've just swapped out what my A's and B's are here. And when I do this in R, I end up with 23,077.72. So how would you interpret this one?
Changing carat from 1.8 to 2.8 yields a $23,077 difference in total price.
Exactly. So a change in carat from 1.8 to 2.8 yields an expected change in Y of $23,077.72. So you'll notice that in both cases we're talking about a 1 unit change because we're talking about the difference between 0.8 and 1.8 and 1.8 and 2.8. But we get different values for what that 1 unit change means because we had different starting places. And since we've got this quadratic function, where we start actually matters. So we can't actually talk about either beta hat 1 or beta hat 2 in the context of a 1 unit change. We have to talk about them in the context of specific differences. So here, the specific differences are between 0.8 and 1.8 or 2.8 and 1.8. So the big picture is basically the beta coefficients, beta hat coefficients that are transformations of the same x variable have to be interpreted together. You must first choose which values of x to change between and then report the change. So you can no longer talk about 1 unit changes in the broad sense. You have to say specific changes in x. And so here I basically just picked 2 numbers. You could do that if you had kind of a reason to pick certain numbers. You might do so. But what people most often do if there's not, if there aren't particular numbers that people care about, often what folks do is talk about a change from the 25th quantile to the 75th quantile. So that's like the first quartile in the data to the third quartile in the data. So you talk about this interquartile range change in x. And so for B, you plug in the 75th percentile. For A, you plug in the 25th percentile, and you report that as your as the values that you're changing between when you're explaining the difference in your y that you're expecting. So the general interpretation for beta coefficients with quadratic terms is the linear term in the model for x has a coefficient of beta hat 1. The quadratic term for the model x has a coefficient of beta hat 2. A change in x from a to b yields an expected change in y of this equation, beta hat 1 times b minus a plus beta hat 2 times b squared minus a squared, holding all other variables constant. And this last part you would only include if you actually had other variables in your model. So here, we didn't have any other variables, so we wouldn't actually need to say that. But if we had, if we were fitting this model instead, because we're holding depth constant, it doesn't actually play into our interpretation of, or our equation, rather, for beta hat 1 and beta hat 2, but we do still need to say holding depth constant if we had that in our model. How do you think this would change if we had like a cubic term, for example? So if we have beta hat 1 times caret beta hat 2 times caret squared and beta hat 3 times caret cubed. How do you think if we were trying to talk about a change between A and B of caret, how would you come up with that value? So this is what we did when we had just a squared term. We did beta hat 1, b minus a plus beta hat 2, b squared minus a squared. exactly. So you would just have this, we'd still have b minus a times beta hat 1 plus beta hat 2 times b squared minus a squared plus beta hat 3 times b cubed minus a cubed. So essentially you would just include all of the functions of the x variable of interest that you have. So for the original model that we had discussed, the interpretation would be the linear term in the model for caret has a coefficient of 2,386 with this 95% confidence interval. The quadratic term in the model for caret has a coefficient of 4,498 with this confidence interval. A change in caret from 0.7 to 1.24 yields an expected change in total price of $6,000.50. And I picked, in this case, this 0.7 and 1.24 as the quantiles, or the 25th percentile and the 95th, or the 75th percentile, rather, of this caret variable. So why didn't I say holding all our variables constant here?
It's not possible.
Yeah, well, it's not possible. There are no other variables besides caret and caret squared, so we don't need to say it for this case. If we had had like depth or color or something else, then I would need to say that. So the big takeaways are the interpretation for a beta hat in multiple linear regression is a 1 unit change in x yields an expected change in y of beta hat, holding all other included variables constant. If the slope differs between groups, so if the lines cross on a scatter plot, that implies that an interaction is present, and you would include that in your model by multiplying the variable for the group by the times the variable by which the slope is differing. And then finally, you can include polynomial terms to address nonlinear relationships, and the coefficients for those must be interpreted together as opposed to being interpreted individually. All right, so let's do an application exercise where you get to practice this. So go ahead and open Apex 14 and fit this model where we include caret, caret squared, and an indicator for the color of the diamond. And then see if you can figure out the 25th percentile and the 75th percentile of caret. There's a function in R called quantile that will come in handy for that. So if you want to read the docs about that, you could do question mark quantile in your console to see if you can figure out how to do that. And then once you've gotten the 25th percentile and 75th percentile, see if you can use it to help interpret beta hat 1 and beta hat 2. And then also see about beta hat 3 as well to see if you can interpret that one. Give you a couple minutes to work on it, and then we will do it together. right, if I want to fit that linear model as specified, what would I do? All right, and let's just look at what this model output looks like. So one thing to note here is even though we had other variables in our model, R still was able to handle this categorical variable color behind the scenes. It created these indicator variables like we talked about last class, where what is the referent category here? D, yes. And if I didn't fit my model, how could what function could I use to help me know what my referent category is going to end up being for a certain variable, just as a reminder from last class? Yeah, I could look at the levels function. And so, for example, I could see that the first value here is D, which indicates that that would be my referent, because by default, R is always going to have the first level be the one it uses as the referent category. All right, so that's from last time. We're interested this time in this part of the model, the caret and caret squared. And so first, let's see, if we wanted to, how do we get the quantile for caret here? Did anybody figure out how to do that? Which function can you use to get the quantiles? Oh, QT. So QT is going to get you, that's a little bit different. That gives you information about the t distribution. So it will give you quantiles of a t distribution, but we want quantiles of this x variable, or this variable caret. Do you know what I mean by quantiles? So like if I were to draw, let me just show you quickly what I mean here. If I were to make a box plot of the variable caret, here, what I mean is I want basically the 25th percentile, which is going to be like this first line, and the 75th percentile, which is this second line. So what I'm interested in is basically the 25th percentile of the data and the 75th percentile of the data, in order to say what a change from being in the 25th percentile of caret would be to being in the 75th percentile of caret. So it's just a way to describe a particular variable. The quantiles are a way to sort of give you some sense of the distribution of that data. So there's a function in R called quantile. Did anybody try it? You can learn more about it by doing question mark quantile. And this tells you that it gives you the sample quantiles for a particular vector. So you put in a vector x and it'll tell you the quantiles. By default, it'll give you the 0, the first, the 25th percentile, the 50th percentile, and the 75th percentile. So let's just try it as specified here. I can do quantile. If I want to do it for the carets, or the caret column, I could pull that out of the diamonds data set here by using the $sign. And so that will basically give me this output that's just a vector of all the values for caret. So if I run that, I get the minimum caret is 0.31 in this data set. The first quartile, or the 25th percentile, is 0.7. The median is 0.9. The third quartile or the 75th percentile is 1.24, and the maximum is 3.35. This function has this probs argument, and so because I'm only interested in 2, I also could just set the probs equal to 0.25 and 0.75, and that would just give me those middle 2 that I'm interested in. The other way to get these values that's sort of a little bit more in line with the type of coding we've been doing so far, this is a quantile is an example of a summary of this data, and so we can use the summarize function where the thing we're summarizing is the quantile of caret, and I can again set the probabilities to 0.25, 0.75, and that would give me the same answer, so this 0.7 and 1.24. So both of these will give me the values that I'm interested in. And so just to sort of visually show what it is I'm doing, let's make a plot of our data. So I'm going to plot the diamonds data on the x-axis. We have caret, that's our explanatory variable of interest. On the y-axis, we have total price. I'm going to do a scatter plot, so I'll use geom point. And then I'm going to add some vertical lines at these quantiles. So I can use the geom v line to add some vertical lines. And basically what I'm doing is I'm saying I want to know what is the impact of going from a diamond that has a caret of 0.7 to a diamond that has a caret value of 1.24. So the impact in y, total price of the change here in x. And in addition to that, I'm going to be using a specific model. The model that I'm using is the one we fit up here. And so I could draw that on my plot as well. I can predict for some new values just to go across this whole range of carets down here. So for example, my caret could be, and my color, it doesn't matter what I put for my color because I'm just interested in basically that change. And then I can get predicted values for these. So I could then add a little line to this where x is going to be equal to that sequence from 0 to 3.5, and y would be equal to the predicted values from our model. And all this is doing is just adding my line here, which allows me to see, basically I'm interested in the slope change in the line from this point to this point. So I just want to know in my predicted y, what is this difference? That's the actual mathematical quantity that we're going to be calculating. And you'll notice if we picked different values to look between, we're going to get different slopes because this is not just a straight line, it's got some curvature to it. So we can no longer talk about single unit changes if we're interested in the thing that's varying as caret, because that is going to have a nonlinear relationship, which is why we're going through this whole exercise. Okay, so I have my quantiles here for this diamond variable. If I wanted to incorporate, if I wanted to get that actual value for that change in expected total price, what would I do to calculate it? Using this equation that we derived previously, what is beta hat 1 here? Yeah, 3205.9. And then what would be B in this case? Yeah, Yeah, 1.24, so I could use that Q75. And what would A be? 0.7. So I would take my beta hat 1 times the 1.24 minus 0.7. And then what would I do next if I were using that equation from this model? I would add 4264.1. Yeah. So I end up with 6,198.25 cents. So what does that mean in the context of this model? What's the interpretation of this 6,198? Yes, exactly. If and there's one other piece, holding. Yes, holding color constant in this case, since that's the other variable in this model. So if my expected, if carat changes from 0.7 to 1.24 for a given diamond, so if I have a diamond that has 0.7 carats and I compare that to one that has 1.24 carats, I would expect that the total price is going to increase by $6,198, holding color constant. So the other way that I could get this would be if I were to just create some new data sets. For example, I could create new data Q75 where I set carat to 1.24 and color I can set to anything. Let's say I'll set it to D for this first one. And then I would create another new data set for the 25th percentile, so it's 0.7. I would leave color the same since we're going to be holding color constant. And then I could predict my value from my model for new data, Q75. And then I could subtract from that prediction what it would be for new data, Q25. And I end up with the same value, 6,198.21. So if you didn't want to calculate all this by hand, you could do it like this, where you just create two data sets and look at the difference between them. And what do you think would happen to this number if I changed color to E, for example? Yes, exactly. It will stay the same because if I run this, the difference between these is going to stay constant. Because that's how we've kind of set that. That's what the interpretation of this is. Now the actual predicted values are going to differ. So for example, here the predicted value is 9,501 for when carat is 1.24 and color is E. If I changed color to I and reran this, the predicted value is 7,019. So the predicted values differ, but the difference between the two predicted values, as long as you've held color constant, will stay the same. So as long as I have the same color, I'm still always going to have 6,198 as my expected change based on this interquartile range change in carat. Any questions about that? All right. So that is it for variable transformations. Let's change gears and talk about comparing models. So we started talking a little bit about how we could compare models a couple classes ago, but we sort of didn't. We're going to continue on that front in the context of multiple linear regression. So often when we're talking about comparing models, at least in the way that I'm going to describe it in this class, we're thinking more about prediction than inference. And so basically we're trying to say, if we're interested in an inferential problem, we're interested in the relationship between some x and y. in which case we're going to be focused on the estimation of that beta coefficient. And in order for that estimation to be unbiased, or basically to be able to quantify the right relationship between x and y, you need to include in your model all of the variables that impact both x and y. And so this is a theoretical assumption and not one that can actually be checked by any statistical check. So there's no way to be able to compare two models and know that one of them is correct and one is incorrect based on any kind of like mathematical justification, which is why these model comparisons are not necessarily for that type of question where you're trying to quantify the relationship between x and y. These are more for when you're trying to predict y from a whole bunch of x's. And so for the methods we're going to talk about today will be different ways to basically, if you fit two different models that have two different sets of variables in them, how can you decide which one is better? So we'll talk about different metrics that you could use to maybe make that type of decision. And so in our toolkit so far, we've talked about the f-test and r-squared for this. And we're basically going to extend this f-test to be a little bit more useful for this context. And then we'll revisit r-squared. And then I'll add two other metrics that you can also use for this type of goal. So far when we talked about an f-test for multiple linear regression, we've only talked about how to compare the full model to an intercept-only model. So basically to answer the question, do any of the x's that we've included in this model or do any of these predictors help us better explain the variability in y? And so the null hypothesis here is that all of the betas are equal to 0. And the alternative is that at least one is not equal to 0. Notice that this f-test, it doesn't tell you which one is not equal to 0. It just is that at least one of them isn't. And so this becomes less useful the more variables you have in your model because you're not really able to tell. All you can tell is this model better than nothing, not is it better than maybe some subset of the model. When we only had one x, this was a useful comparator because we could say basically is including this predictor better than not. But now that we have multiple x's, it becomes potentially less useful because we're comparing it to a pretty puny baseline. Basically, the baseline is that we just didn't do anything. We didn't use any variables. We just have an intercept-only model, so we basically just took the average value of our outcome y. And we're seeing if we can add any information by adding all of these variables, which maybe is too broad of a test. But in that circumstance, what we had talked about before, that F statistic is going to be that mean squared model divided by the mean squared error. In the context of multiple linear regression, what would the degrees of freedom be for this numerator, for the model? K, exactly. It'd be the number of predictors in our model. And what would the degrees of freedom be for this denominator for the errors? N minus k minus 1, exactly. All right, so we're going to talk about a nested f-test for multiple linear regression. And here, nested means that basically you have a small model and a large model where the small model is completely contained within the large one. And so in the example of the f-test that we've done so far is basically an extreme example of this nested f-test because the small model includes 0 predictors in it and the large model includes all of the predictors in it. And so what we're basically saying is that we can extend that same concept to instead of forcing it to be either 0 or everything, we could have something in between. So our smaller model might include 5 variables as opposed to 0, and our large model would include all k of the variables. So the f-test we've learned so far is one example. We're comparing this intercept-only model, so a model that only has beta 0, that's our small model, to this large model that has all of these x's or all of these predictors, all k of them. And so here, the full or the large model has k predictors, and the reduced model has k minus p predictors. And so the difference in number of predictors between these two is going to be p. So in the case of the f-test that we've done so far, p and k are the same because we had 0 predictors in our small model and we have k predictors in our large model. So they end up having the same value. So the full large model has k predictors. The reduced model has k minus p predictors. What do you think the null hypothesis is for these nested models. What is the null for the normal for the original F test that we did? It's that all the betas are 0, right? So, and if in this case we're saying that instead of having the comparator be one with no betas or no x's, maybe we would have a couple. So, for example, if we had just beta 1 and beta 2 in our small model, our large model then would have beta 1, beta 2, beta 3, all the way up to beta k. And so, how would you think? If you're kind of comparing those two, what would need to be equal to 0 for those to be equal? All the other beta coefficients, exactly. So the null is basically that all the beta I equals 0 for all the p predictors that are dropped from the full model. So the predictors that are in the full model but not in the small model, we're assuming that all of those are equal to 0. And then what do you think the alternative is? Exactly, at least one is not equal to 0. So the question we're asking is, does the full model do a statistically significantly better job of explaining the variability in the response or in the outcome compared to the reduced model? So that's what these nested F tests, that's the question that they're able to answer. So the F statistic is slightly different now for the F for this nested one compared to what we were looking at before. Now, in the numerator, we have the sum of squared model for the full model minus the sum of squared model for the reduced model divided by p, where p is the number of predictors different between the full and the smaller model. And then the denominator is the same. It's still that sum of squared error for the full model divided by n minus k minus 1. So in these 5 models, which of these are nested within each other? Yes, 1 and 2 is nested, and so the difference between 1 and 2 is that 2 has this interaction between x1 and x2, whereas 1 just has a coefficient for x1 and x2 as opposed to also that interaction. Are there any others that are nested? Yeah, 2 and 4, and also 1 and 4. So 4 is just only has x2 in it. And so this is nested within these two, exactly. All right, so let's say we take these two models. I've got y equals beta 0 plus, this should say beta 1 times x2. And then in this case, I have beta 0 plus beta 1 x1, beta 2 x2, beta 3, and the interaction between these. So comparing these two models, what is p here? Yes, exactly. It's going to be, those would be the two that are extra. P is just equal to 2, but those are the two that we're interested in. We're interested in this beta 1 and this beta 3 here. And what is K? 3, exactly, because the bigger model has 3 variables, it's factors it's estimating. Okay, so here is a specific example. I am trying to predict the weight of a fish based on their length and width. And I have two model proposals. So I have a measuring tape, but not a scale, and I'm trying to figure out how much these fish weigh based on some previous data. So I'm interested in this prediction model. In my first model, I have length and width and the interaction between the two. And in the second model, I have length, width squared, width squared, as well as the interaction. So is the first one nested within the second? Yes, it is, because all of the variables in the first are contained within the second, and then some, because I've got these two extras in the second model. So if I were to write out the equation for model 1, what would it be? Yeah. So this is my model 1. We've got beta 1 times length, beta 2 times width, and what did I do? And beta 3 times the interaction between length and width, plus our error term. Our second model is going to be the same as this first part. So we've got beta 0 plus beta 1 plus beta 2 times width plus beta 3 length times width. But now we have two extra variables. We've got beta 4, which is going to be times length squared, and beta 5, which is going to be times width squared. So what would my null hypothesis be if I were to do an F-test comparing these two models? Yeah, beta 4 equals beta 5, which equals 0, so that both of these are equal to 0. When we're talking about null hypotheses, we typically don't put hats on them because we're saying that this is the assumption that the truth is that these are not equal to 0, which is why these don't have hats. And what would my alternative hypothesis be?
At least one, either beta hat 4 or beta 4 or beta 5.
Exactly, that at least one of them, so either beta hat 4 or beta hat 5, or not hats, just beta 4 or beta 5 are not equal to 0. Exactly. So here I've written as 3 and 4, depending on where, it just depends on kind of where they end up in your model equation. But all right, so what are the degrees of freedom for this test if n equals 50? So we said our F statistic is going to have 2 degrees of freedom. We're going to have numerator degrees of freedom and denominator degrees of freedom. What would the numerator degrees of freedom be for this test? So 5 would be k, but the numerator's degrees of freedom is actually going to be p. What is p in this case? 2, exactly. So our numerator degrees of freedom will be 2, and what about our denominator degrees of freedom? Yes, 56 minus 5 minus 1, so n minus k minus 1, which is 50. So the 2 degrees of freedom are 2 and 50. And so we can get the numerator and denominator of this F statistic by using the ANOVA function. And so now, because we're in multiple linear regression, we've got multiple lines here. We've got one for each of the predictors in our model. And so we have a line in our ANOVA table for length, one for width, and one for length times width, the interaction between the two. If we add up all of the sums of squares for each of those predictors, we would get the total sum of squared model, the overall sum of squared model for model 1. So adding those up, I get 6,544,329 is the sum of squared model for model 1. So that was by adding these three numbers, which are the three sum of squares for those three predictors. For model 2, I have 2 additional predictors here, so I would add up all 5 of these to get the sum of squared model for model 2, and I end up with 6,553,094. And then this is my equation for the F statistic. It's that sum of squared full minus sum of squared reduced over P times the sum of squared error full over n minus k minus 1. And so this first part here, the sum of squared full minus sum of squared reduced, is going to be that SS model 2 minus SS model 1, so 8,765. What is P here again? 2, exactly. So I would divide by 2 to get 4,382. And now we've got our numerator of our F statistic. And looking at this output, where can I get the denominator? Where can I get the sum of squared error full? What is the sum of squared error in this output? So the sum of squared error is always going to be this last one that is associated with this residuals line. So in this case, it'll be this 93,000. And then what about the degrees of freedom for that we're dividing by? What would that be? Yeah. So putting all of that together, our F statistic is 2.36. And now, what are we usually comparing this F statistic to? Like, how do we calculate, for example, a p-value for this F statistic? When we were doing just a normal F test, how would we get a p-value for the F statistic? Yeah, so we would try to find, this would be the value that we observed, and we would try to compare that to what it would be under the null, and then we would quantify the probability that you'd see either this or something more extreme given that null was true. So in this case, the degrees of freedom are going to be 2 for the numerator degrees of freedom and 50 for the denominator. And so we could do that same, we're going to use that same method to compare this observed statistic, this 2.3, to an F statistic under the null. So to do that, we just use the PF function. You plug in what you got for your F statistic, and then you plug in your degrees of freedom, so 2 and 50. And we end up with this 0.105. So how would you interpret the 0.105 here?
Probability of getting the F statistic more extreme than the one we get from here equals to 1.
Exactly. Yeah, so the probability, given
The null hypothesis.
given the null hypothesis is true. Exactly. So the probability of seeing an F statistic as extreme or more extreme than 2.36, given the null hypothesis is true, is about 10%. So it turns out we did a lot of hand calculations to get that. It turns out there's an easier way. The ANOVA function takes multiple arguments where you can put in the two models. So you put the smaller model first and the larger model second, and it will do this F test for you. And so we get that same, when I do that in R, I get that same F value of 2.36 and the same P value here of 0.11. So this compares these two models and calculates an F statistic as well as that probability. All right, so are there any questions about nested F tests before we move on to R squared? Okay, so that is one way to be able to compare two models. If you had two nested models in mind, might be a good choice to be able to decide which one you ultimately want to use. Another very common metric is R squared for multiple linear regression. We covered before that this is just the ratio between the sum of squared model and the sum of squared total, which we could also write as 1 minus the sum of squared error divided by the sum of squared total. And so as is, if you just use this metric, if you add a predictor to your model, it will always increase your R squared. And so that's where R squared adjusted comes in, that basically has this small penalty for adding more predictors. So R squared adjusted basically, we refer to this as a metric that basically gives you some measure of goodness of fit, but also allows for your model to be parsimonious, meaning that you're not just kind of including more and more and more predictors, you're only including them as they're actually useful for the model itself. So at some point you would stop adding predictors because the marginal utility would be small. And so R squared adjusted is slightly different than R squared, just in that it divides by the degrees of freedom in both the numerator and denominator when you write it in this form. And so now we're taking the sum of squared error divided by n minus k minus 1, divided by the sum of squared total, divided by n minus 1. And so we talked about this last class, but the sum of squared total over n minus 1 is just the sample variance. And this numerator here is just the mean squared error, so another way to think about R squared is it's just 1 minus the mean squared error over the sample variance. So basically we're just adding in this slight penalty so that it's possible to get a smaller R squared adjusted when you add an additional variable, which is not possible for regular R squared. So the denominator here is going to stay the same for all models fit to the same response variable in data, but the numerator will actually increase when a new predictor is added to the model if the decrease in the sum of squared error is not sufficient to offset the decrease in the error degrees of freedom. So what that means is that the R squared adjusted can actually decrease when a weak predictor is added to the model. So this makes this kind of a better choice for when you're comparing models. R squared adjusted is generally the one you want to use since it has this slight penalty. So it sort of has this balance between model fit and parsimony, which is what we tend to be going for. So here are my two models. I've got model 1 and model 2. My multiple R squared is 0.985 for model 1, and it's 0.986 for model 2. R squared adjusted is 0.984 for model 1 and 0.985 for model 2. So strictly speaking, model 2 has a greater multiple R squared and R squared adjusted compared to model 1. However, in this case, if I were looking at this information, it doesn't, the change is not very, it's not very large, and in fact, both of these are like very, very high R squared values. You almost have perfect prediction, which suggests that these particular fish, it's very easy to guess their weight based on their length and width, so there must be a pretty consistent relationship between those and how much they end up weighing. So if I saw this output, I probably would tend towards model 1 because it's a little bit smaller and has basically the same R squared or adjusted R squared. So the model comparison criteria, basically we're looking for a reasonable way to balance goodness of fit, how well the model fits the data, with parsimony, how many variables we've included in our model. And R squared adjusted basically gets at this by adding this penalty term for adding additional variables. There's two other metrics that we're going to talk about in the next couple minutes, AIC and BIC, that also balance goodness of fit and parsimony. And so they basically also give you some sense of how well the model fits the data, while adding a slight penalty for the number of predictors you have in order to make sure that you're not just kind of continually adding more and more predictors. Because you can imagine, so in the extreme case, if you had some data, let's say I have some data that looks like this, and I want to fit a model between X and Y, if I could find a unique variable, for example, an ID for each person where I could basically draw a line between I could basically connect the dots, that would be the best fit model for this data, but it's probably not very meaningful if I were trying to predict a new value, and it's definitely not parsimonious. And so these metrics are basically trying to help balance between kind of, in this particular case, just drawing a line to this data probably would be sufficient, and a model comparison criteria that basically takes into account the number of variables that you're looking at in addition to the how well the model fits the data. Kind of having that balance between both of those is nice. So both AIC and BIC, they rely on this quantity known as the log likelihood, which is essentially some measure of how well your model fits the data. The actual, this is what the log likelihood, this is the actual value of the log likelihood. It basically comes from the fact that we're assuming some normal distribution, we have normal distribution assumptions underlying our model, which is where these actual values come from. But the thing that I basically want you to remember is that this log likelihood is a function of the sum of squared error, which is something that you have seen before. So basically the amount of variability that's not explained by the model, as well as the sample size n. And so this log here that I'm referring to, this is a log-based E, and R, you just use the log function to get this. There's a function called log likelihood that will get this value. You're not going to need to use this function, but just to sort of show you that this equation that I am telling you is the same as what the actual log likelihood would be. For model 1, for example, I could use the log likelihood function and I get negative 290 as the log likelihood, or I could plug into this equation that I gave you, and again, I get negative 290 there. So this is a goodness of fit measure. It gives you some sense for how well your data fit your model fit the data. Higher log likelihood values are better, so bigger values are better. And both AIC and BIC are calculated using the log likelihood. So what I want you to remember about the log likelihood is that this is a component of both AIC and BIC. I want you to remember that it is a function of the sum of squared errors and n along with some constant. It's a goodness of fit measure, and that higher numbers are better. These are the pieces I want you to remember. You don't have to memorize the equation for it, for example. So AIC is one of these metrics. It's Akaiki's information criteria. This is just the person that first published about this method. And so what it takes, the equation is 2 times k, the number of predictors, plus 1, minus 2 times the log likelihood. So lower AIC values are better. You can calculate the AIC of the model using the AIC function in R. And so knowing that lower AIC values are better, would you pick model 1 or model 2 based on this output? Model 2, yeah, because model 2 is a slightly smaller AIC. Now again, in this particular case, these models are so similar, their R-squared values were so similar, that if there were a compelling reason to pick one or the other, I might kind of just pick the one that's easier to fit as opposed to using this because these are so close. And you can see how close they are because if you use BIC, which is a different type of criteria, you actually see the reverse model suggested. So BIC stands for Bayesian information criteria. It's very similar to AIC. The second part is the same, minus the log likelihood, but the penalty is slightly different. it uses the log n times k plus 1, where again, k is the number of predictors in the model, and lower BIC values are again better. If I were using BIC, which model would it tell me to pick? Model 1, yeah. And so the difference is because this penalty term is slightly different in both of these. And so how would you pick if you were to see something like this kind of out in the wild, you were trying to decide what model, you look at AIC and BIC and they give different answers. Both are valid. What I usually recommend is to pre-specify. So before you fit any model, say which one you're going to use and then just stick to that. So you'd pre-specify if you were going to use AIC or BIC. Or if you state that you'd like to look at both, kind of specify a preference so that you kind of know which direction to go in if you end up in the circumstance where they are similar. The cases where they are similar often mean that the two models, there's really not a strong difference between the two. So you might pick the smaller one in that case, just because often that would, if they are so close that you're getting kind of similar comparisons regardless of kind of which one you pick, then maybe the smaller would be a more parsimonious choice. Okay, so in our toolkit now for comparing models, we have F-tests, which allow us to compare nested models. We have R-squared, which allow us to compare any two models, and we have AIC and BIC as well. At the start, I'm not going to start an application exercise since you only have a couple more minutes here, so we'll start this next class. You will practice doing this yourself, where you fit a couple models and use nested F-tests as well as AIC and BIC to compare these models. All right, are there any questions before we head out? All right, thank you.